Okay, so I think this is alternating series, and I hope that you have at least observed some exercise on the attachment in the model. Okay, let's continue. Okay. That this will be 11.6, which is the ratio and root test. Okay. The ratio test is one of the most practical method, okay, in chapter 11. Okay. Aside from a divergence test, okay, ratio test is oftenly used to check the series. Okay. But let me write the ratio test first, okay, and let's see what we can do to apply the test. Maybe I will write in terms of take the limit. So basically, ratio test is we are just take ratio between an plus 1 and an. And we need to find some number L. And this L can be less than 1, greater 1, and L equal 1. Okay. If L is less than 1, that means that the series is absolutely convergent. Okay. Because we limit the ratio with the absolute value. So when L is less than 1, it should be absolutely convergent and therefore convergence. If L greater 1, we will have or if the limit is infinity or doesn't exist, then is divergent. If L equal 1, the ratio test is inconclusive. No conclusion. So no conclusions can be taken about the convergences or divergences. The idea behind this ratio test, if you look on how these three components are, is actually based on or similar to what we have in geometric series. Okay. So in geometric, we have the ratio, right? We have the ratio. And the ratio will determine how the series will be. If the ratio is in between some numbers, okay, between -1 to 1, if you remember the geo series, you will have the converge, right? Okay. So let me apply this ratio test for some applications. Okay, so some examples. Okay, so if you have this seems to be an alternating series which has the -1 with power of n, okay, and the component is having a fractions n cubed divided by 3 with power of n, okay. If you take some time to check questions from this ratio test, okay, this 11.6 and maybe later in 11.7, if you see some series that has this kind of property, which having some power, so some power having the n, this is actually a takeaway to give you an idea what we have if we take the ratio test. Okay, so imagine this series and imagine the n+1 of this form. Okay, imagine if you exchange n with n+1. Okay. So this is actually a quite obvious series that we might want to try the ratio test. Okay, so if we try to the ratio test, okay, so maybe we can try to define first. Okay, define the an+1, define an, and since it's absolute value, we can cancel the -1. Okay, so we are focused only the n+1 cube, or maybe we can just skip this and divide by an. This will be 3 with power of n and n cubed. And now you'll see clearly that we can cancel this 3 with power of n, okay, and it's left with 3, okay. And now we have 1/3 n+1 over n and then cube. We can write like this. And if we take the limit as n approach infinity, we will get the idea that the n, the limit of this n will be 1. Okay. Now we have this is 1/3. The result is 1/3, which is less than 1. That means we are having absolutely convergent series. But sometimes, for some cases, we are having some failure, okay, or we fail to take a conclusions. For example, some simple series like 1/n or 1/n squared. Let me just 1/n squared. If we take the ratio test, this has become n over n+1 and then squared. If we take the limit, this will be resulting in 1, which is we are getting nowhere. So if we get the 1 as our result, it means that it's inconclusive. And of course, 1/n squared, we can just take the p series, and because p is greater than 1, which means that the series is converged. Okay. So for some simple cases like this, ratio test might not work. Okay. So that's the brief example on the ratio test. Okay? And I think it's one of the most practical methods. Also, we are going to use a lot later in 11.8 for ratio test. So you should be able to be more get used to the test. Okay. Another test that is similar to ratio test is called the root test. And root test is more obvious than ratio test. Okay? Because you are going to have the method is by taking the square of some n, and you need to take it and get the result of L. Okay? And this L, similar to what we have in ratio test, it can be less than 1, greater than 1, and equal 1. And the conclusion is similar. Okay? So if it is less than 1, then it should be absolutely convergent. Converge. Or maybe or limit does not exist, then the series is divergent. And if this equal 1, it's inconclusive. And because of this form that taken this square, which means that the series should be an obvious series. For example, if you have the series with power of n like that. This was an obvious example that you need to take the root test. If you see any series that has the power of n, or maybe 2n, 3n, or any n, which means that the more you are looking at this series, the more you are getting towards to just use the root test. If the idea is to take the power and remove the power. So if you take this, and by taking the n of absolute value of an, this will leads to 2n plus 3 and 3n plus 2, which we have, if you take the limit, we will have 2/3, which is less than 1, and we know that this will be absolutely convergent. Okay, now we have additional ratio tests and root tests. And from these two examples, now we have completed at least several tools, okay, several methods to check our series. Okay. And this will lead us to some strategy for testing the series. So let me do some review on how we can take this testing as a guidance, okay, a strategy. And the strategy is not restricted. I mean, you can choose which method you prefer. Okay. But in terms of inconvenience, the practical and the most or the easiest method for the logical order, you need to start with divergence test. Okay, and take the limit of the sequence. And to get direct result, it needs to be not equal to 0 or it doesn't exist. And then you can determine directly this will be diverged. If it is 0, it's not converged, okay? It's not necessary to be converged. Remember, if you take the limit and it's equal 0, it's not necessarily to be converged. You need to confirm with other methods, okay? You need to confirm. But if this happens, then this will be diverged. Let me write so you don't forget. So if limit 0 means that not necessary to be converged, need to be confirmed by others or other methods. Okay, so first differential test, okay? The most practical test that you can do at the very beginning to check your series. Second and third is if you see any P series from the series that you are going to test. Okay. So check whether it's going to have like 1 over n with power of p. Okay, and then you can check the p. Have converge, diverge. Okay, if not P series, maybe geometric series. Okay, maybe you can take the series and make it into the form of sum A, or maybe using blue. Sum A R n minus 1. And remember that you have the ratio less than 1 and ratio this is converge, diverge. Okay. 4 is probably comparison test. So if you check divergence test, no conclusions, and it's not P series, not geometric series, then you can try comparison test. I believe comparison test is also practical and not too complicated to be checked. And you can have direct comparison test or using the limit comparison. So you need to define a series of AN and a series of BN, and then you check the limit comparison test of AN over BN. And it needs to be a positive number. Should be a positive number, so that the series should be both converge or both diverge. Okay? And probably can also think about alternating series. But sometimes alternating series also obvious because it has the negative one. But not all negative one can be treated as or can be tasked by the alternate series. Okay? You need to make sure that this value getting smaller and the limit is getting 0. So this has two components, that is bn plus 1 is less equal bn, and the limit of bn should be equal to 0. If this satisfies, then we have a convergent series. Okay? And also in alternate series, you have several types. Okay? You can have the absolute convergent, conditional convergent, and also divergent. Okay? So suppose this alternating series, you can also think at the very beginning. Okay, if you look upon the series, and number 6, we may have the root test. But sometimes if you're familiar with some series, the root test can be also not root test, sorry, ratio test. Some ratio tests can be also taken, and maybe you can directly go to ratio test directly. So as long as you can take the ratio between the an plus 1 over an, okay. Maybe, and if you take the limit, remember L less than 1, L greater than 1, and L equal 1. This is converge or absolutely convergence. This is diverge, and this is inconclusive. Or doesn't exist. Then the last two methods that is not really that practical is the root test and the integral. Root test will be useful if the an is having power of n. Okay? That will be very obvious because you can take the root with power of n, and you can cancel the power of n immediately. An integral test, this will be also useful if we can think the series as a function, and we can think the function as we integrate from 1 to infinity, or in the improper integral. This is easily integrated. If not, then we can just skip the integral test. Okay? And also what we need to have in integral test is the function here for the an need to be always decreasing. First is continuous, it need to be of positive functions, should be decreasing on 1 to infinity. Okay. Why we need to have positive? Because we want to have precisely area under the curve between the axis and the curve. Okay. So if the curve itself not positive functions, then we are not really, we cannot sure how we can integrate and calculate the area under the curve. Okay. So integral test means that you need to identify the series or identify the sequence in the series as you are maybe imagine if it is, or if the series was integrated. So you need to try and check, okay? And also before that maybe you can check the series. They need to be decreasing. They need to have positive functions. Okay, perhaps we can have some overview on how we can use all this strategy. So maybe we have some examples. So probably we have some example. So let me give you maybe 2 or 3 questions. Maybe start with the number A. Okay. And then maybe number B. Let's start with the simple one first. So what's for A? Vector or factor? What's for the first one? Okay. Okay. Some obvious uh, obvious form. Okay, if you look on the series like this, if we can just look on this n and n cube, okay, if we can imagine with some other functions or some series that is probably having n and n cube, or probably we have the 1 over n squared. Okay, perhaps we can try comparison. Okay, we can try the comparison. Okay. So we can try comparison and look on how the n minus 1 over n cubed plus 1, and if we can make this to be more, if we can compare this, okay, so compare one by one. Perhaps we can start with less than n cubed plus 1, okay, and we can take this into another level, that is a cube, or this is 1 over n squared. Okay, I think this is logical, right? Okay, so I think we can take this as our approach. Okay? We can take this to check the series with the comparison with 1 over n squared. And since it's less than this 1 over n squared, and 1 over n squared is the convergent series by P series. Okay? So we can write, since the series converges, let me remind you that this is a P series, P is greater than 1. Okay, so this will be resulted in n minus 1 n cubed plus 1 also converges by direct comparison test. Well, if you would like to track back what you did, probably you can check the limit, and if you check the limit, it's 0, right? And we can't conclude anything with limit equals 0. So then we can, maybe if you look here, it seems that it has this plus 1 and minus 1. And the obvious takeaway is, if this has happened, and if you think you can make another set of series, and you can compare it with this, then you can take them to a direct comparison. If you check direct comparison, and maybe you think the comparison is not really that true, you can take to the other one, the other method, the limit comparison test. That is when you cannot really prove that this is true. You can check the limit comparison test. Or if you check limit comparison test right away from here, sometimes it can be helpful, sometimes it's not. But since we can take the direct comparison test right away and see the logical order here, we can just take this to direct comparison test. Okay, now we take our time for the second one. Any idea? Even without any calculation, you should be able to tell. within seconds. You should be able to tell. Unless you are telling that you need to find the value. Unless. But you should be able to tell within seconds. Can you tell within seconds? Is it diverge or converge? Yes? Yes. Why? Okay. Any other reasons? Okay, remember that the series, you can split the series. Okay? So you can think this, the P series, with T equal to, which is converged. This is geometric series. And both of them are converged. So you can see this and just tell, okay, then this two is converged. Because this is a converge, this converge, we can say that this is a P series, or let me write that this is can be written as 1 over n squared and plus. Okay, so we can say that this will be a geometric series, and this will be a P series. So the series conclusions is convergent. Okay, maybe giving you more, maybe 2 more examples. Maybe that is the first one. And maybe the second one is okay, we have these 2 other questions. The first one is -1 over n. ln n divided by square root of n, and the second one is n sine 1 over n. If you want to try the second one first, I think because it's easier to check. So since in the series we will deal more with limits, so I hope you still remember some limit laws, some limit property, how to solve limit. Okay. Which includes some techniques on derivative also. I hope still remember. And later at the break, I will give you your results. Please. I think most of you did pretty well. How about the first one? Anyone? Fine. So what is number one? The first one? See, convert or divert? Any other answer? Convert or divert? Since the first one having -1, since it has the -1 with power of n, maybe we could try to check with the alternating series. Okay, we check with the alternating series. Okay. So check the alternating series. So alternating series. What we need to check is we need to prove that this two has been applicable. Right? So first, to make sure that the order is true, that it's always getting smaller and smaller, and since it's just ln n divided by the square root of n, and if you didn't bring any calculator with you and you need to observe and make sure it's decreasing, remember that in calculus 1 you have the way or the method to check whether the function is increasing or decreasing, which is we can just derive this. So check so remember that if this is an fx, so this is worth to remember. Okay, this is increasing, this is decrease. The same way, if you want to check whether the function can be integrated or not, you can also check with the first derivative to check whether it's increasing or decreasing. So we find the first derivative, we find through this quotient rule, right? So we will have, or if you don't remember how, let me just write the formula for you. Okay. This will be 1 over n, and then or if you want to make it into x also, okay, I would think. If you want to make it into x, so maybe to differentiate between our calculations. So this will be 1 over x, square root of x, minus 1 over 2 square root of x ln x, and divide by x, and we can move down and then simplifications, and this become we can multiply with 2 over 2, which will be 2 minus ln x, and we move down, it become 2x with power of 3 over 2 x square of x, right? And we need to find when this should be a decrease. So this will be decreasing when less than 0. So this is the statement. So we can have this ln x should be greater than 2, or x should be greater than e squared. So this will be decreasing for e squared and then the second one we check the, let me go down here. The second one we can check through the limit Sn approaching infinity of ln n divided by square root of n. So to solve this, we need to check with L'Hopital rule, because this having indeterminate form, right? So we have 1 over n and 1 over 2 square root of n. So we have limit 2 of square root of n, which is 0. So by both of this, it's decreasing and it's going to hit 0, then the conclusion will be the series is converges by alternating series. Okay, we will have yeah, I think most of you did pretty well, or at least above 55, 60. I think that should be fine. Okay. But if you at least work out all the questions, like from number 1 to number 5, okay, and know how to solve, not really getting the final answer, but at least to show the process, I think it should be around 60 to 70. It should be 60 to 70. At least you know how to, and you know the process. Okay? And if you complete all the answer, then probably you have like 90 to 100. Okay? Some mistakes, some miscalculation, that's still okay. I just maybe deduct a few points from that process. As long as the whole process, the big process, is relevant and correct through the answer, then I think for most cases you will get at least higher than 70 at least. Okay, now we are going back to this number. Okay, so the previous one is convergent series. It's converged by alternating series. Now the second one, we have n and then sine 1 over n. Okay. Now as this strategy mentioned, like I previously stated, that we can take the limit. Okay, we can take the limit. Let me close. Okay, anyone maybe have tried converge or diverge? Diverge. Okay, that's good. Okay, so perhaps we can try the limit itself. Okay, for the sequence. So we can take this limit. Okay. Now remember, in limit, especially for sine, remember that if you have, right? Okay. Now we can also use these examples, or if you like, we can also take this into other form as well. This is similar forms, right? Okay. So by looking at this sine 1 over n, what we can do is actually we can try to multiply, or maybe divide this with the n and 1 over n, like that. Okay. Now we have limit as n approaching infinity. Now we have sine 1 over n and divide by 1 over n. Okay. And this will result in 1, which is not equal to 0. That means we can take a conclusion: the series diverge by divergence test. And directly we can answer this. Okay. Okay. Okay, so that's a little bit of some examples. Okay. How to use the testing, the method, the test, okay, for some series. And for some parts, you will see that some series are quite obvious, okay? And you can just observe the series and look how they behave and how they can be, maybe you can change the form and manipulate the form and look on how the series can be tested. Okay, now we are moving to another section, okay, which is called the power series. And the power series will be related to ratio test that we did at the beginning of the class. Okay. So the power series let me start with the definition first. Okay. So power series is the series in the form of, we have a constant, okay, C. So if we have a constant and we have some power, okay, some variable x, with power of n. Okay, so we can take this and write down the expansions. Okay, that's the expansion of the power series. Okay. This is constant or coefficients. We can also call this coefficients. Now if we take, okay, if our coefficients is just 1, okay, we can take the series as just x with power of n. Okay, and if we start from n equals 0, this will be, the expansion will be from 1 plus x squared plus x cubed plus, okay, and we know that this is, if we imagine this as a geometric series, we will have a common ratio that is x, right? Okay, then the common ratio. And if you remember that it will be converges when it's, or maybe, yeah, from -1 to 1, this will be convergent. And diverge, if we take this will be divergent. Okay, so imagine that if you exchange your x, okay, maybe x becomes 2. So if x becomes 2, then it means that it's diverged. Okay, if x is half, then we have the geometric series which is converged. Okay. Now, as a general general form of this power series, we can write in terms of in more general. It's not just only x, but it's x minus a with power of n. Okay, so from 11.2, 11.3 until 11.7, we learned how to determine the series converge or diverge. We are just looking on the formula, and we have the n as the integer of the sequence and series. And now we have another variable, which is x. So this x means that your convergent series might have an interval. So it's not just point out on one single point of convergence. So you have a series of interval, a set of interval of the convergence. So you might have some x that range from maybe 0 to some numbers, okay? Or maybe from negative numbers to some positive numbers as well. Okay? And what our goal in this section and in our series, we want to find what's our interval of convergence. That's the goal, the idea. If we have the set of x. So, I think we can have some definitions. Just a simple definition: that power series in x minus a means that this is power series that's centered at A, which means that if we take that as an interval, it seems that we have, if we imagine like a circle, we will have some radius, okay, some radius of interval, and that radius is actually what is represented in x minus a, okay, the distance. So this is a. Now let me give you three examples on the power series and what our conclusion by those three examples. Okay, let me give you one by one. Okay, so the first example, what values of x does the series converge? So to determine the values of x, usually in the power series, we are going to use the ratio test. Okay? The ratio test that we did in the previous lectures. So we check the an plus 1 and an. We check the ratio. So this will be x minus 3, n plus 1. This will be n plus 1 divided by an. We will multiply, cross multiply. Okay. And from here, we can cancel x minus 3 with power of n. And we are going to have x minus 3 and then n plus 1. Okay. Or if we try to take the limit of this n, the limit result is basically equal 1, right? So this is resulted in terms of absolute value of x minus 3. Okay? Which means we are going to have bi-ratio test, if we are trying to write it completely, the series will be converges when this result is less than 1. Okay, remember this, the requirements in ratio test: less than 1, greater than 1, okay, and equal 1. Okay. So we may have our interval of x that is ranging from 2 to 4. But it's not finished yet. Okay, it's not our final answers. We need to check the other interval. Okay, maybe we can write the divergence first. Okay, so the series diverge when this x minus 3 is greater than 1, or we can take this into x less than 2 or x greater than 4. Okay. Now the last one is the inconclusive one, right? If we have x minus 3 is equal 1. So we must consider that x is equal 2 or x equal 4. Okay. The next step is we are going to check x equal 2 and x equal 4 into our formula. Okay, into our formula. So we are going to put x equal 2 to x minus 3 with power of n. Okay. And it's become negative 1, right? If we check with x equal 2. So we are having the series that is negative 1 divided by n. Okay, and if x equal 4, it's going to be 4 minus 3. It's just 1, right? It's just 1 over n. Okay. One over n is the harmonic series, right? If we check with P series, also is n equal 1 is divergent. Okay. But this one is converged, right? Alternate series is going to be less, and it's going to be the limit going to be 0, and we know that it's converged. So this will be convergent. This will be divergent, which means that when x equals 2 is convergent. So this should be equal. It should be included in the conclusion here. So the final conclusions should be this. Okay. So the series, or maybe let me write at here, then the final conclusions, the series, the given series converges for 2x 4. So we need to include number 2. Okay. So it's step by step by taking the ratio and then use the conclusion from the ratio test, which has 3 conclusions: less than 1, greater than 1, and equal 1. If the question is asking you just to observe the convergent, then you can focus more on the convergent and it's equal also 1. Okay. And then check back to the original question and looks or observe what the series is going to be. What will be the series, and from there you can check whether it's converged or diverged. So this is the first example, the first possibility, okay, for the power series. At least we will have 3 possibilities. Okay, 3 possibilities. So this is the first possibility. Let me make number, this is first possibility. Okay. Okay, now the second one, okay, the second one The question is still the same, but the series is now x with power of n. Maybe this one first. N factorial and x with power of n. This is example 2. Okay, now we just, for starters, we are going to use the ratio test. Okay. Now remember factorials. Okay, the factorials, just a note to remember that if you have n plus 2 factorial, this means that this will be n plus 2, n plus 1, and then n factorial. Or if you have n plus 1 factorial, this will be n plus 1 and n factorial. Okay. Okay. Now, if we have this n plus 1 factorial, means that it will be n plus 1 and n factorial. So we can cancel this n factorial. And then we can cancel this x with power of n. This is x. Oh, I think I make a mistake. This is not the form. Should be x n plus 1 here. So this will be cancelled. This will be cancelled. Okay. Now we will have n plus 1. Or maybe let me write x first. X and then n plus 1. And we take the limit for n plus 1. Now, if we take the limit, this turns out to be an infinite limit, right? We will have an infinite point. So, in order the series to be converged, what is going to happen with x? What values of x? So that the series, the whole thing, going to be converged. Okay, this limit is infinite. And what happened with x? What is our value so that the whole series will be converged?
0.
Yes, 0. Okay. So x should be 0. So if x is not 0, then the series diverges. The series converges only when x is equal to 0. So this means that we only have a single point, okay, single point of convergences, which is x equals 0. Okay, now the third example is this. So let me write this is third example. So again, take the ratio test. So we take the an plus 1 divided by an. this will be 2n plus 2. Okay. Factorial. And 2n plus 2 will be 2n plus 2, 2n plus 1, and then 2n factorial, right? So we can cancel this 2n factorial. And we have canceling this and x. So we have, this will be x, and then we have 1 over 2n plus 2 and 2n plus 1. If you take the limit, the limit for this n will be 1 divided by infinity, right? If we multiply, this is going to have like 4x squared, and just notice that it's going to have 1 over something n, it's going to have a 0, right, as a result. Which means that the whole limit here will be 0, which means every x you put in, every x you take, it will also be converted. Okay. By the end of the day, it's going to be 0. So all x will be converged. Okay. So all x will converge. So the given series, here, the given series converges for all values of x. Okay. Now, as a conclusion from 3 examples that we have, from these 3 examples, I think we can take this, put it right here. So a theorem, okay, theorem. For power series that is start by Cn x minus a with power of n, there are 3 possibilities. The first one, the series converges only when x equal a. The second one, the series converge for all x. The third one, there is a positive number r such that the series converges if x minus a less than r, and diverge if x minus a greater than r. Now this r is the distance that we are talking about, and the whole thing will be an interval. Okay. So we have r as our distance, or in our definitions in the power series, r will be the radius of convergence. And the interval of convergences we can write in terms of a minus r, a plus r, and we will have 4 possibility. Okay, you may observe this in terms of this my number here. This will be the distance, the radius. This is the whole. So we might have 4 possibilities of interval. That depends on the series that we observe. Okay. But at least from this one, you get the at least idea that in power series we are likely to see how the convergences in our series. Okay. How is our radius? Okay. If there is a radius, how is the interval? Okay. If it's only a single point, then there is no radius. The distance is 0 because it's just a single point. And we may have the some summary, okay, for the example that we did before. If we take the picture, okay. Now if you look here, the radius of convergence is 1. You may have conclude this radius from the form. Okay. If you see an x minus 3, and if you take the ratio test and the result maybe x minus 0, x minus 4 plus 5, x plus 2, it's an obvious way to see that because it's only a single x, that means its radius will be just 1. If the result 2x minus 1, 2x, means that if you solve that x, the x will have a half. Okay. That means the radius probably becomes half. Yeah, 3x as your result after you take the ratio test. Then your radius will be 1 over 3, 1 over 4. It depends on this x. Okay. If this happens, the second one, in a single point, there is no distance, no radius. You can say the radius is 0, and when x equals 0, that is just our convergence, our interval. And if all x included means that the radius cannot have any interval, right? Cannot have any distance. It's all included. We can have an infinite point of radius. Or in the interval, it's going to have all values of x. Okay. So let me give you maybe one example. So for example, if we have a sum okay, and the first step for all power series, we take the ratio test. Okay, we take the ratio test, and we observe the radius of convergence, and we find the interval of convergence. Okay. So maybe the question is find R and interval of convergence. The first step is we always have the ratio test. We can cancel this part. This will be having -3. So we will have, this is 3 and square root of n plus 1 and square root of n plus 2. Or maybe we can take this into one big square root. Okay, and we take the limit. Of course, the limit will result just 1. Okay, it will be 1. Oh, I forget the x. The x is here. Okay. So it will be resulting in 3 with absolute value of x. And then remember the conclusion on ratio test. So this will be converge if it's less than 1. So we will have less than 1/3. That means our radius becomes 1/3. So we can also say that the radius is 1/3. Maybe we can write also for the diverged one. And then from the interval of convergences, we know that it will be between -1/3 to 1/3, but we need to check. Okay, we need to check when the x is equal 1/3. Okay, so we need to check maybe right here when x is 1/3, or maybe we start with the -1 first. Then we will have, we are going to exchange x with -1/3. This is -3 and 1/3 and negative. Sorry. Okay. Now the series becomes, this will be canceling each other. Then we will have 1/square root of n plus 1. Which this will be diverged, right? This will be diverged because it's a p series. The p series. We can also look on the p series. This is p series with p is less than 1. So this will be diverged. And then we have x equal 1/3. We will have, this will be -1 with power of n, and divide by square root of n plus 1. And we know that because it has -1 with power of n, and the series seems to be getting smaller for the value, and the limit itself is equal 0. So it will be converged by alternating series. Okay, converged by alternating series. And thus, the conclusions will be given that the interval of convergence is, we can write, and we need to include 1/3, positive 1/3. Okay. So the idea, okay, the first one, ratio test, and from ratio test we have 3 conclusions, right? Less than 1, greater 1, and then equal 1. So for less than 1 it should be for the convergent one, greater 1 is the divergent. For equal 1, then we need to check, okay, each case. Okay. We check for negative 1/3, we check 1/3, and check each series, which one is divergent, which one is convergent. Well, it can be both divergent, it's also happening, it depends on the case. It can be also converged, both converged. So you need to check one by one. Okay. And then after that, we are writing the conclusions of what we find, the interval of convergence. Okay, any questions? Any questions first? The discussion. If not, we'll have a small review on chapter 11. Okay. Hope you don't mind. Let me go through. If you need to have some notes over here, or you can take some notes first if you want. Maybe giving you maybe 1 minute if you want to write some notes. If it's okay with you, then we are going to have some sort of small quizzes. We have been doing this for some time. I forgot to create for the chapter 10 for the polar one. Should be doing that for the polar one. I give you small questions, so I hope you can answer the questions. And maybe you can use your student ID, okay, student ID as your name. If you have difficulty to join through the QR code, you can, I think, go to the website and entering the code. Okay, I think we can start. And I hope the time is okay. I have 4 questions. And all the questions just having two possible answers. For now, we can just choose which one. But for the exam one, you need to prove some statement or maybe some equation. I think this is when we have the sequence one, the really first introduction. Okay. 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 Okay, get ready. Okay. I hope time is fine and sufficient enough. 1.5 minutes. maybe next Monday I will explain some of the questions. Oh, let me just start the question 3, okay? Remember, we had some similar one before, so I hope you can do something, okay? Do not be intimidated by this complex. You can imagine this k is 1/3, right? This k half. So you can imagine with some series, right? Could be. And if you pay attention for the k, you can do it in your head if you really pay attention to this. Okay. Okay. Let's see. Okay, ET taking the throne. Okay, good. ET taking the throne.
I just changed my name.
Okay. Okay, good. Okay, negative sign 1. Sign 1 you can predict and assume.
Oh no. Oh no.
You need to get whether it's convergent or divergent. And because it's already stated it's convergent, and if divergent you need to write the false. If it's true, then just write true. Oh.
我想错了，一开始我就想错了，然后我就整个就按下去。
The key is later using the P series.
挖下去。
Okay, taking the throne. 27, who's 27? Okay, taking the throne. There are 2 survey, okay? Just a simple survey after this. Okay, please fill in the statement. If you disagree, going to the left. If you agree, going to the right. And I just want to know some small survey from you. If you agree with the statement, then you can go over to the right. If you are like so, maybe middle. Maybe if you disagree, then go to the left. Okay.
Quite helpful. 没有，我也没有，我没有都中间。
While you're still writing, there's one more. Still one more. Okay, you can make some suggestions or maybe anything that you want to improve from our course.
他说是我传给他，跟我觉得我也是被别人传染。
对啊，你也感冒了。对。
那我感冒。
我们单试了一下。
又是我。
哦，明天晚餐是吗？那我等一下。
Okay, some YouTuber, yeah. Okay, that's also good. I think you can take a lot of examples for other sources.